Good morning, everyone, and welcome to this talk about color. So how many of you think they understand color? Raise your hand. Nobody? OK, I guess that's why you're here. So I gave a similar talk last year at NDEV 360, and there was a lot of math and a lot of equations, and a lot of worried developers asked me if there's going to be math in this presentation. There's going to be no math, no equations. Instead, there's going to be physics. So let's talk about color. The first question we have to ask ourselves is, what is color? It sounds like, a deep question. The answer is not so deep. So here's a definition that applies to most of us as human beings. We're not developers, we're just regular people. So it's a visual perception that can be described by hue, brightness, and colorfulness. Sometimes colorfulness is also called saturation. And if you've ever used the HLS, HSL, or HSB colors in the Android APIs, you might be familiar with that kind of definition. What's really important to understand is that color is just a perception of our brain. It's not a real thing. And we're going to see why that is. So obviously, we see colors with our eyes. And if any of you see colors through another mean, I would love to talk to you. And to understand how we perceive color, we first have to go back probably to high school or college and try to understand what light is made of. So I'm sure most of you know that light is made of photons, but there's a duality to light. It can be a wave or a particle, and we're going to look at the wave nature of light first. So light is an electromagnetic wave, and our eyes are just receptors for those electromagnetic waves. So here's the electromagnetic spectrum. It's not to scale. And from the shortest wavelengths to the left to the longest wavelengths to the right, we have in order the gamma rays, the X-rays, the ultraviolets, the visible spectrum, that tiny little bit in the middle full of colors. Then we have the microwaves, and the infrared, the microwaves, and then the radio waves. The part that interests us is that it's that tiny bit in the middle. So that's what we call the visible spectrum. It goes from about 400 nanometers to 700 nanometers. And all of us, these are the only wavelengths that we can see. Why does this matter? Our eyes, like I said, are receptors. They're actually made of millions of small receptors called cones. Most of us, almost everybody, has 3 types of cones that can detect different parts of that spectrum. So you see the spectrum here at the bottom. Those are all the wavelengths of colors that we can see. And this diagram shows in 3 different colors the sensitivity of each type of cone that we have in our eyes. They're called short, medium, and long. Sometimes they're called blue, green, and red. It's not technically accurate to call them red, green, and blue. So instead, we're going to call them short, medium, and long. And they're called that way because the short ones help us see in the blue wavelengths, so ultraviolets, violets, and blues. Then we have the medium ones that help us see the greenish colors, and the long ones that help us see green, orange, yellow, and a little bit of red. And you can see there's a lot of overlap between the medium and the long receptors. So now, what is light? So light is a distribution of several wavelengths. So this is what we call the spectral power distribution of a light bulb. So the kind of light bulbs that you can find in any house. It's an orangish light bulb, and you can see the amount of energy it outputs in different parts of the visible spectrum. And you can see here that this type of light bulb outputs most of its energy in the red and orange part of the spectrum, and that's why we perceive it that way. But what happens when the light from that light bulb hits our eyes? So we saw that we have those receptors. They have different sensitivities, so different parts of the spectrum. So we just multiply the distribution of the incoming light with the sensitivity of our different cones. And the result is what we perceive. So when we multiply both, we get this. So when you look at one of those light bulbs, you see almost nothing in the blues. You see a little bit of green and more orange and red. And then our brain will interpret that as an orange color. The way we actually interpret the result of those cones is a little complicated, and we don't have time to go into the details here. You can go look on Wikipedia how it works if you're interested. So here's what happens exactly when we look at a light source. The light is emitted by there's wavelengths emitted by the light source. It hits our eyes, we multiply by the cones, and that's what we perceive. But most of the time, you're not looking directly at the light. You're looking at different objects that surround us. And how do those objects get their color from? So every object also has what's called a spectral power distribution. It's a description of the wavelengths that the object can reflect. We call that the reflectance. So some of the wavelengths will be absorbed. So for instance, a black object absorbs almost everything that's incoming, and a white object will reflect pretty much all the wavelengths. So we also multiply, to perceive the color of an object, what happens is that we have light coming, it bounces off an object, some of it is reflected, so we just multiply the two distributions, then it hits our eyes, and we get the final perceived color. What's very interesting here is that any combination, because it's a multiplication, any combination of light and reflectance can yield to the same perceived color in our brain. So a very simple example is that if you have an orange object lit by a white light, you're going to see it orange. But if you have a white object lit by an orange light, you're also going to see it orange. And our brain does a lot of post-processing, really, to help us understand what is the color of the light, what is the color of the object. And a few years ago, there was this famous example of the dress. Some people were seeing it in black and blue, some people were seeing it in gold and something else. And that's exactly what's happening, is that some of us were interpreting the result differently. And nobody was wrong. It's just without the context, you can't really know for sure. So yeah, we can swap the colors, the distribution of the light source and the object, and we're going to see the same result. So that leads us to something called the chromaticity diagram. It was standardized in 1931 by the Commission Internationale de l'Éclairage, CIE. It's French commission, apparently. And it represents all the colors that we can perceive as human beings. So on that horseshoe shape, the outside edge is called the spectral locus. It represents all the pure colors, the pure spectral colors, so that spectrum of colors that we saw in the previous diagrams is actually bands around that edge all along. And everything in between, all the colors that we can actually see, are a mix of all those different wavelengths. Then, so it has that weird shape. It's not a rectangle or anything. And there's a lot of colors that live outside of that spectrum. We call them the imaginary colors because we cannot see them. No matter how hard you try, you won't be able to see those colors. There are some optical illusions that you can find online that will kind of help you find those colors. It's actually really weird. Not everybody can see them or perceive them. There's one, for instance, where it shows you a blue rectangle for one of your eyes and a yellow rectangle for your other eye. And the way I see it is this really weird color that you can't really describe that keeps changing from blue to yellow but never stops on one of those two colors. The visible spectrum is actually a little bit more complicated than that. What you're seeing is a slice. It's a 2D slice. There's a z-axis that's coming towards you, and that is the brightness. So the footprint at the bottom, like this large footprint you see, is the dark colors. It's because our eyes are better at seeing dark colors than they are at seeing light colors. So we've seen what colors are for us as human beings, but everybody's a developer, I think, in the audience. So the real question is, what is color for us as developers? What does it mean for your application? So color really is an encoding scheme for brain sensations. And the formal definition is that it's a tuple of numbers or list of numbers defined within a color model, and it's associated with what we call a color space. And we're going to look at some examples to make you understand that. So here are some of the color models that you might be familiar with. RGB is one of the obvious ones. I'm sure everybody's used that. CMYK, if you have ever printed a picture or a book or something, you might have also dealt with it. And there's another one, for instance, called LIB. There are others. There's XYZ. There's many others. What's interesting is that the color model defines how many numbers we need to define a color. So you're used to RGB, it has 3 colors, it has 3 values, but CMYK requires 4 values, for instance. So the one that we're interested in today is the RGB color model. It uses a triplet of values, hence the name, and you are mostly, I'm sure most of you or all of you are familiar with the hexadecimal notation. So there are many ways of representing that tuple of numbers. This is one of them. It's pretty popular, especially on the web. You've probably used it a lot on Android when you want to pass a color directly to one of our APIs. So this is a pinkish color. So this is the same color represented as a triplet of 8-bit unsigned integers. You're also most likely familiar with it. This is something we use a lot on Android when you set the color on the paint or when you use the color.red to extract the red component of a color. This is another notation. This is actually the one I prefer. This uses floats. So the values are between 0 and 1. And it's interesting because it's more versatile. You can use it to represent HDR colors. And we'll see that Android actually makes use now in O of the float notation to have negative colors and colors that go beyond 1. So to reproduce colors, so the big question is, once we have those numbers, what colors do they actually represent? So I told you this is a pink. But you've seen that spectrum of colors. There are many, many, many pinks. There's actually an infinity of pink. So which one of those pinks does this represent? So to reproduce colors, all of our displays use additive light. So we use red, green, and blue. And our TVs, our phones, our computers, our old CRT monitors, and they just mix those different lights. So the numbers that you just saw, the RGB triplets, it might sound obvious, but they're an intensity for each one of those lights. So let's say we pick 3 lights. We pick a green light, a red light, and a blue light. And they're not perfect spectral lights. They're just random lights that you found. They are found somewhere in the visible spectrum. And together they form a triangle. So when you have an RGB color in your application, you are just, you can only represent one of the colors within that triangle. You cannot represent colors that live in the entire visible spectrum. So, and that triangle is what we call a color space. And there's an infinity of them. Depending on the 3 lights you choose, you can represent any of an infinity of color spaces. So here's, for instance, the widest, or one of the widest color spaces we could create. The problem we have is that with a triangle, with just 3 lights, we cannot encompass all the visible spectrum. We have to choose a smaller slice. So this one in particular is called the Adobe Wide Gamut RGB color space. There's no device that I know of that can capture or recreate this color spectrum, this color space. And the problem is that if we wanted to create a color space with RGB that contains all the visible colors, we would have to create lights that are in the imaginary space, so lights that we cannot perceive because we've seen that our eyes cannot perceive outside of that horseshoe shape. But color spaces are a little more complicated than that. So color spaces are actually defined by 3 components. The first ones are called the primaries. There are 3 of them. Then we need a white point, and then we need something called transfer functions. So this might look like a complicated diagram, but what I did is I've put the visible spectrum on the left, and I've overlaid 3 triangles that represent 3 common color spaces that are used for still images. So the smallest one you see in the middle, the blue triangle, is the one we call sRGB. I'm sure you've heard that term before. So sRGB stands for standard RGB, and it was designed in the 90s, and it kind of matches the reproduction capabilities of the CRT monitors of back then. And to this day, it's still used everywhere, and it's pretty much the universal color space, the only color space that you can count on. There are other color spaces. There's Adobe RGB, for instance. It's the orange triangle. Because it's bigger than the sRGB color space, we say that it's a wide color space, or it's a wide gamut. So the 3 vertices of the triangle is something we call the gamut. And then there's something called Prophoto RGB that you can see extends beyond the visible spectrum. And this is not a color space that we use to actually represent colors on the screen. This is what we call a working color space. For instance, when I take a picture with my camera is set to Adobe RGB, so it captures everything in the color space that you see on screen. Then when I import my photo in Lightroom, internally, Adobe Lightroom works in Prophoto RGB. And it won't be able to recreate all the colors that it's working with on screen, but the idea is to have as much precision as possible. So you can ignore this kind of color space for your needs on Android applications. So I said a color space has 3 primaries, and the primaries really are the coordinates of each one of the 3 vertices of a triangle in that chromaticity diagram, in the visible spectrum. So they identify, when you say, for instance, that you want a color that's red equals 1, green equals 0, blue equals 0, it tells you what red we're talking about. And if you look here on the screen, sRGB and Adobe RGB, when you say red equals 1, they have the same exact red, but Prophoto RGB has a different red. So it's 2 different reds for us, not necessarily for our computers. We'll take a look at that. And then we also need a white point. And the white point is the same idea. It gives us the coordinates of white in that color space. And we'll get back to that. So I also mentioned transfer functions. Transfer functions are a little bit complicated. That's where a lot of math comes into play. You've probably heard about them under the name gamma. So if you heard about gamma correction, that's actually transfer functions. So I gave a talk last year about transfer functions. I don't have time to talk about them today. I'm gonna show you a link at the end of the talk. If you're interested, you should definitely go look at that talk. There's a lot of things that you should learn about transfer functions that can impact your applications. So I've been talking about color spaces, but why do we care so much about color spaces? So the problem is that every device out there has a different color space. So for instance, you can have a phone that has an LCD screen and is going to be close to sRGB. You have a phone that has an OLED screen and it's going to be closer to P3, to a color space called P3, or to the Adobe RGB color space that we just saw. And same thing for your laptop, for your computer, for your TV. And things get even worse, because even if you have two phones, they're the same model, there's the same manufacturer, they're both supposed to be, let's say, P3, there are variations in the manufacturing process, so they won't be the exact same P3, so the colors won't be exactly the same on those two devices. I'll show you an example of what happens. So let's imagine that we have content that we created for sRGB, so it's in the sRGB color space. We designed it at home on our computer that shows sRGB colors. That's the white triangle you see. And then, if we take that content as is, we don't do anything to it, and we just show it on a display that's Adobe RGB, what we're going to do is we're going to just take those RGB triplets, those values we had, and reinterpret them in a different color space. So suddenly, your green that you had in sRGB, like that green equals 1, is going to be a different green. It's going to look completely different to your user who's using an Adobe RGB screen. So here are concrete examples. This is a photo I took. I took it in Adobe RGB. I processed it in ProPhoto RGB. I converted it nicely on my calibrated monitor to sRGB. This is what it should look like. Actually, this is not what it should look like. On my laptop, it's what it should look like, because those screens have a color space. I have no idea what it is, but it's definitely not sRGB. And what you see is really wrong. But what matters is the difference between the next photos. So let's say that this is proper sRGB. This is how I wanted you to see the picture. Now, if I display the picture as is on a different screen, let's say DCI P3, it's going to look like this. So if I go back and forth, you can see there's a difference in contrast. Some of the colors are a little bit more saturated. So already, my photo does not look like the way I intended. Then if I display it on a ProPhoto RGB display, if such thing existed, it would look like this. So super saturated, really garish. I don't know about you, I really don't like this picture. And those are only when that happens when we only affect the primaries. But you can have similar issues when you affect the white points. So the next slide here, that is the same sRGB photo, so we kept the primaries, but I changed the white point to something that's bluish. And suddenly my photo, well, you know, it's underwater, so it kind of makes sense to be blue, but it is not the way I wanted it to look like. So again, if you take multiple Android devices, for instance, and you put them side by side, chances are that some screens will appear yellow to you, some screens will appear blue to you or green, and that's because of the white point. We have different white points across multiple displays. And once again, the same model of device from the same manufacturer, there are going to be white point variations. So when this happens, we say that colors are unmanaged. This is what Android has been doing since Android 1.0. And I hate it, absolutely hate it. It's horrible. You know, your designers will spend hours and hours like slaving away on their computer, like creating a beautiful UI. Then you test it on a phone, and it looks completely different. And you test it on another phone, and it looks completely different again. So you might be thinking, how can we have our design look exactly the way we want? So the solution is something called color management, and it's new to Android O. So the idea is that every color that we want to display needs to be associated with a color space. We need to know what was the original intent of the design. So we need that information. Then through the magic of a lot of math and matrices, it's actually more complicated than just a matrix, but that's most of it, we're going to do a controlled conversion to the destination color space. So what we're going to do is that when we manufacture a device, we're going to use special devices that will measure the capabilities of the display. We're going to measure the primaries and the white point of the device. We're going to create the destination color space. And then we can convert your original content to the destination color space and preserve the same colors that you wanted to have. So this is something we're introducing in Android O. And there are two parts of it. There's first color management proper, and then there's something called the white color gamut rendering. And we're going to take a look at both. But first, before you need to worry about Android, you need to make sure that you or your designers are using color spaces properly in your design application. And there are two things you can do with pictures. You can assign a color space, or you can convert a color space. So I'm going to switch to a demo. But first, I just wanted to show you, earlier I said that color spaces, this chromaticity diagram we had, the horseshoe shape, it's a slice of a color space, and so are the gamuts, those triangles. So this is sRGB in 3D. And it's interesting because I mentioned that our eyes see more in the darks, and you can see that in the diagram. The brighter the colors, the fewer hues we can perceive. All right, so for the demo, so I'm using a tool called Affinity Photo. And this is a picture I took, same process. I took it in Adobe RGB. I was using raw files from my camera, from my DSLR. I used Profoto RGB to do my work in Lightroom, and I created an sRGB version of the picture. And if we zoom in, pretty much any good design tool somewhere will show you the color space of your image. So here we know it's an sRGB image. I'm on a calibrated display, it looks fine. And like I said, you can assign a color space, often called an ICC profile, or you can convert. So if you assign, what you're saying is you're just saying, keep the colors the way they are, keep the same values. I just want to move them to a different color space. So let's say we move to the Profoto color space, and now it looks like this. This is exactly what Android does. This is not the right way of doing it. Sometimes that's what you want because you know what you're doing, but very often it's not going to be what you want. So instead, what you want to do is to convert ICC profile. It's sometimes called match. So we pick Profoto, and when I click, you'll see no difference. And this is what we wanted, but what happens is that every single RGB value has changed. It just looks the same, we just have different values stored inside the image. And to give you an idea of what happens to your Android design, so this is a screenshot I took of my Pixel 2016 running Android N. And on Android, we pretty much assume that all the content is sRGB, so when I opened this file in the tool, I was warned that there was no color space and that the tool would assume sRGB. Now, when you display this screenshot on an OLED display, because we don't manage color, what happens on my Pixel 2016 is this. So I hope you can see the difference. If you look at the red icons at the bottom, you can see that everything becomes more saturated. So that's what you designed, and that's what you see on an actual phone. All right, so when you don't know what the color space is, just assume it's sRGB. It's the only assumption you can make. And this is why, like for instance, all my photos are sRGB, because when I put them online on the web, I have no idea what display you're going to use. I have no idea what device you're going to use. I don't know if your app is going to be color managed or not. And sRGB is your safest bet. It won't be always correct, but it's your safest bet. So when you use a design tool and you have a color picker, if there's no information about the color space anywhere in the tool, you are most likely using either sRGB or what we call a native gamut, which is whatever the screen can do. For instance, this is what Apple Keynote does. When you pick a color, you pick the color directly for your display and not another display. If your application is color managed and your document has a color space, you're picking a color in that color space. Some color pickers are more advanced. So this is, for instance, on macOS Sierra. If you click that little gear in the second tab, you can choose the color space you want to use for the color picker. And actually, when I was working on the slides, I picked colors for the slides, and then I was creating diagrams into a different tool, and I tried to match the colors, and I forgot that I had to change to sRGB in this speaker, so it took me 5 minutes to understand why my colors were different. So even when you know about color spaces and color management, it can sometimes be confusing. Another tool you can use on Mac, on macOS, for instance, and other platforms have similar tools, is the Digital Color Meter. It's in the Applications/Utilities folder. It lets you pick any color on the screen, and using the drop-down, you can choose the color space you want for that color. So you can look at the color in the native gamut of the display, or you can use sRGB or P3 or whatever. On Android, if you have a recent version of Android, and if you have a Pixel device, for instance, if you go to the developer options, you can turn on the sRGB mode. So here what we're going to do is apply color correction. We're going to apply color management to the display to make sure that all the colors are interpreted and reproduced as sRGB. You might be surprised at first, a lot of people complain that the colors looked washed out, but they're actually more accurate. It's just a matter of habits. All right, so now some code. So on Android, what you've been using so far is what we call the color int, just an int. It contains alpha, red, green, and blue. And the only assumption we can make, because we don't know what color space you're using, is that it's sRGB. So it's pretty simple. Now in O, we're introducing a crazy new API. We've had that color class for 10 years, but it only has static methods. Now you can create instances of the color class. You can actually use color as the way it was meant to be. So you just call value of, you give your RGB values, and that's going to give you an instance of the color class in sRGB. Because note, I didn't specify the color space, so my assumption is it's sRGB. You can also specify the color space. So here we also call value of. We pass the alpha, so the order is RGBA when it floats. And then we say that we want that color to be in the Adobe RGB space. What this allows us to do is work with colors so we can convert them from one color space to the other. So I have this Adobe RGB color, and if I call convert, I can convert it to display P3, for instance. Someone's happy? Something else we're introducing, so color ints are really useful because they're easy to manipulate, they're small, they're easy to store. And color objects, the color class is very generic. It can represent colors. It uses a float array internally. It has a reference to a color space, so they can be pretty heavy objects. So now we have something we call the color long. It's the same idea as the color int. We use a primitive type to store a color, but we also store the color space for that color. So it's similar to value of. You just call pack instead, and you get a long. And here's the format of the long. So we have 16 bits for the red channel, 16 bits for the green channel, 16 bits for the blue channel, we have 10 bits for the alpha channel, and then we have 6 bits that identify one of the built-in color spaces. And those 16-bit values, they use something called half floats. So they're floats that use only 16 bits instead of 32 bits. So there's a new API in O called android.util.half that lets you manipulate half floats. Anybody who does HDR or advanced rendering in OpenGL or Vulkan might find that API useful. If you use the color class, you don't have to worry too much about it. There's a ton of utility methods on color that will use the half API on your behalf. So we also have the color space class. It's well documented. It's pretty easy to do. You just call get, and you can create one of the common color spaces that we provide. You can create your own color spaces if you want. Two methods that are interesting on color space. There's isWhiteGamut. It will tell you if it's a wider gamut than sRGB. And getModel, it will tell you how many components are in that color space. So RGB, CMYK, LAB, stuff like that. If the model is RGB, you can cast it to colorspace.rgb. That gives you access to more APIs. You can query the primaries, you can query the white point, you have access to the transfer functions. This is also very well documented. If you want to do conversions between color spaces, it's pretty simple. You call connect. You give us the source color space and the destination color space. And the reason why you need to call connect is that we need to make sure that both color spaces use the same white point. So when the color spaces have different white points, we do a little bit of math internally to turn them into the same, to make them use the same white point effectively. So then you need to call the transform method. You can give us RGB values, and we're going to give you back the corrected RGB values. You can also change the white point of a color space. So if you call adapt, colorspace.adapt. So here, for instance, we do what I did for one of my examples, my photo of the fish that was very blue. We took the sRGB color space, and I changed the white point from something called D65 to something called D50 that's bluer. White points are usually defined as a color temperature. It's the perceived color of a black body when you heat it to that temperature. So here, D50, it's 5,000 degrees Kelvin, and it's blue. And D65, which is a very common white point in color spaces for our monitors, it's 6,504 degrees Kelvin, and it's more yellow. Bitmaps, we now support color spaces embedded in bitmaps, so they're called ICC profiles. Until now, we would just ignore it completely on Android. So if you use Bitmap Factory to decode a bitmap, now you can call get color space on the bitmap, and we're going to tell you what it is. Most likely, for most images you're going to load, and presumably for all your resources that come inside your APK, the answer is going to be sRGB. So you can call color space that is sRGB to check what kind of color space it is. And that's very important. All the bitmaps on Android are always in the RGB color model. We might expand on that in the future, but we don't let you use LAB or CMYK or XYZ or any of that. They're always RGB. So you can, right now, when you call get color space on the bitmap, you can always cast it to a color space that's RGB. It might not be future-proof, so just make sure by checking the color model. You can do more interesting things with Bitmap Factory. So on bitmapfactory.options, we have this horribly named field called in just decode bounds. It was originally created to let you query the dimensions of an image without having to decode all the pixels in the image. So it's really quick. It gives you an idea of how big the image is going to be. Over the years, we've kind of abused this field. So now it's going to tell you the configuration of the bitmap. Is it ARGB 888? Is it RGB 565? And now it also tells you what the color space is. So if you want to know the color space of a bitmap ahead of time, you have to ask us to give you just the bounds, just the dimensions. So you call your decode method on Bitmap Factory, you pass your options, and then we have this field called out color space that tells you what is the color space of the bitmap. So if you want to make sure that the bitmap is in the right color space before loading it, you can do this. And if it's not in the right color space, you can use this other API on options called in preferred color space, where you can tell us what you want the color space of the decoded bitmap to be. So in this example, for instance, let's say we queried the color space of the bitmap. We saw that it was Adobe RGB. I don't want Adobe RGB. I want sRGB. So I can use in preferred color space to force the system to convert it at load time. Then you can just call decode. We're also introducing in Android O 16-bit bitmaps. So they're bitmaps that use 16 bits per channel. And those bitmaps are always in a color space called linear extended sRGB. And we're going to take a look at what it is. So when you have a 16-bit bitmap, don't try to convert the color space. We're not going to let you, at least for now. This is how you create a wide gamut bitmap. You just call create bitmap. You specify the width, the height, the configuration. The Boolean tells us whether there's alpha in the bitmap, and then you just give us a color space. So pretty simple. Bitmap has APIs that let you read and write pixels inside the bitmap. So because getPixel and setPixel use color ints, they have to use sRGB. So when you call getPixel on a bitmap that is not sRGB, we're going to do a conversion for you. Same thing when you call setPixel, we expect sRGB, so you have to do conversion yourself. Now, if you use this other API called copy pixels to buffer, it gives you access to the raw data of the bitmap. So that data is going to be in the native color space of the bitmap, left completely untouched. You have to be a little bit careful because of that new configuration for 16-bit bitmaps. So if you load the 16-bit PNG, the data in that byte buffer is going to be half floats. It's not going to be those color ints. And that's why you might want to take a look at android.util.half. All right, so now what happens when you draw bitmaps on the screen? So until now, what we are doing is we take a bitmap, we assume it's sRGB, we send it to the screen, and if the screen is not sRGB, too bad, the colors are going to be completely wrong. This is still what we do by default on Android O. Now, if we have a bitmap that we know is not sRGB, it has a color space associated with it, we're going to do an sRGB conversion on your behalf in the rendering pipeline. It can be a little bit expensive, so you should avoid it as much as you can if you don't need non-sRGB bitmaps, but at least the colors are going to be correct on the display. Now, if you render a bitmap into another bitmap, so if you create a bitmap, you create a canvas, and then you call draw bitmap on that canvas, we're going to convert from whatever the source color space is to whatever the destination color space is. So if you want to convert a bitmap from one color space to another, not at load time, this is the way you do it. You just create the destination bitmap, you create a canvas, and you just draw. So pretty simple. So we make all those assumptions about sRGB, but like I said earlier, if you remember, I said that OLED displays on our phones have wide gamuts. They can show more colors than sRGB. Now the problem is that if we take your sRGB content and we don't stretch it to the entire gamut of the display anymore, and we keep it in that little triangle, we have all those unused colors that we're not taking advantage of. So in Android O, we're adding this new API, and it's super complicated. It's just one attribute that you add to your manifest per activity. you have to tell us that you want to render using those extra colors. You want the white color gamut mode. The way it works is as follows. So if you have sRGB content, if you're on a device that does not support that mode, not all devices will support that mode. So if you're on a device that does not support that mode, your window is going to use the ARGB 888 format. That's what we've been using for 10 years, so there's nothing new there. You have your sRGB content, we just draw it directly on screen. If you have non-sRGB content, we convert it to sRGB and we send everything to the screen. Colors might be wrong, but that's just because the device does not support the new white color gamut rendering. On a device that does support white color gamut rendering, we're going to make a much larger window. We're going to use 16-bit per channel, so it's going to double the size in memory of your window. It's going to double the needs in bandwidth. So it is an expensive thing. So if you don't really need white color gamut rendering, think twice before enabling it. If we have sRGB content, we're going to send it directly to the display as well. And if we have non-sRGB content, we're going to convert it to a color space called extended sRGB. And what is extended sRGB? It's a kind of a weird color space. It's a really big color space. It's way bigger than the visible spectrum, much, much bigger. And some of the values are negative, and some of the values are greater than 1. They go all the way to 7.5. And what's interesting about that color space is that all the values between 0 and 1 match exactly the sRGB color space. So what it enables us to do is we can take your existing content, all your sRGB content, basically everything you have in your app today, and we can draw it directly. We don't need to do any conversion because it's going to match sRGB. So what we do is we only pay the cost of a conversion when we're drawing non-sRGB content. So we have, the expense is that we need 16-bit per channel because we need a lot of precision and range to be able to encode this sRGB space. But it's much better for you. It's much simpler. You just have one attribute in your application. Interestingly, because we use 16-bit per channel because of extended sRGB, we can, or we will be able to, maybe in the future, to render in HDR directly. So we could have HDR user interfaces. We also have a new resource qualifier called white-CG for white color gamut. So you can create layouts or strings or drawables that are specific to a display that supports the white color gamut rendering mode. We also have a few APIs that you can use to query whether the device supports white gamut. So if you have a resources instance, you can grab the configuration, and the configuration will tell you if you have a white color gamut display. If you have a view, you can call getDisplay. We give you a display object, and you can ask the display whether or not it's white color gamut. So the main conclusion of all this is don't panic. I put a bunch of hearts on the slides to make you feel better about all this. I know it's complicated, and no matter how hard you try, and I don't want to sound disheartening, but your colors are going to be wrong somewhere for someone. Like, they're wrong for me on that screen. And I know a little thing or two about color spaces and color management, but you're not in control of everything. You're not in control of the final display, and you're not in control of all the software that intervenes in the pipeline of an application of rendering colors. So don't worry too much about it. Do your best. Make sure that your designers work on calibrated displays. Make sure they work in sRGB. Make sure the images contain color spaces, and you should be OK, or at least mostly OK. So if you want to learn more about transfer functions, so there's this talk I gave last year with Chet. So if you go to that URL and you go to minute 29, that's when the color part of the talk starts. The first half is about animations. It's also super interesting. You can also look at the documentation for colorspace.rgb. There's a lot of details and information about transfer functions and what they mean for you. If you want to learn even more about colors, I gave a talk at Devoxx US a couple months ago. I talked about bending and dithering. What is bending? How can you fight it? What do we do in the platform to fight it on your behalf? So if you're interested, go at that URL, and it starts at minute 36. And I think that's it. I only have 1 minute left, so I don't have time for questions, but I'll be at the Android Sandbox if you want to talk more about color and color management and all that. Thank you.